It's my name. Coming to the US, I realized
the Swiss connection.
The Swiss connection. So coming to the stage show in Switzerland, I realized, that you're technologically more advanced in something. So I have this green laser pointer where I can still constitute my elitarian geek status in Europe, and here everybody has it. So I'm going to have to get a blue or a purple one or something next time I come. So anyway, I think I'm going to switch gears a little bit and drop down in the second half of my talk on some software engineering issues. But I do want to show you the motivation for starting and continuing to work on IPLT. And the key word here is collaborative. Now, the European Union is rich, and they're pumping a lot of money into EM right now. There is a 3D EM network of excellence that includes 60 labs, and it's really a push to advance methods and usage of electron microscopy, tomography, single particle, and electron crystallography. Now, one of the work packages is dedicated at the 2D electron crystallography methods development, and it encompasses 4 labs, starting north with Stockholm, the group of Hans Keber, then we have Frankfurt, the group of Werner Kühlbrand, and there's Basel, the group of Andreas Engel, and in Madrid, the group of José María Carazzo. And this group has set out with a rather ambitious goal, and which is also a little bit provocative in this context, namely, we want to revitalize 2D electron crystallography to solve structures of membrane proteins at atomic resolution. I will gladly be discussing this over lunch or dinner in the following days, why it needs to be revitalized. Because I'm of the firm opinion that there are still some things wrong. And on the first day, we had these issues about detergent and lipids and purity, and if that's really the bottleneck. So that might be the bottleneck, but I'm thinking there's also other bottlenecks. So our strategy is the following. We want to, and we are, re-evaluating all existing algorithms. That basically means the whole MRC package is not taken for granted. And we are going to, and we are implementing the proven ones. Now we are also redesigning the software from scratch. We're looking at MRC, what they did, what we like about it, what we sort of not so much like about it, but we're also looking at the vast structural biology field, especially X-ray crystallography, what sort of they're using. We're also rethinking development and collaboration strategies, and Henning gave this beautiful example of Henderson taking the software off the server. And that's obviously sort of the opposite of collaborative. And finally, we are very, very interested in developing and implementing novel methods. And actually, we should solve some structures on the way to prove that this is all worthwhile.
As you say, Andreas, rethink his mind.
Yeah, so this slide is usually to please my boss, and since you're taping this, and he's going to watch it, I have to put this in, that we really want to solve some structures.
I don't think there's the time to watch it. He's too busy.
Now, I get furious when people accuse me of reinventing the wheel. There's no reinvention of the wheel. This term does not exist. We are redesigning the wheel. As you can see here, starting from a primitive wheel, it is vastly necessary to redesign all the time. Now, you're not going to have a space shuttle land on this wheel. So I have to stress this over and over again. We're redesigning, building on existing stuff. Now, what have we done and what is left to do? Breaking down the processing based on previous experience and concepts, and putting it into fairly independent subprojects. That's done. Design and implement a dedicated, tailor-made software for exactly the purpose of implementing and re-implementing. That's pretty much done, and you will hear about that. Provide basic classes and algorithms. That's pretty much done. Now, these three we're working on daily. Embed or re-implement the existing 2D electron crystallography algorithms, code new approaches, and implement, on top of that, the processing flows. What you showed Henning in the beginning, when to do the FFT, when to create the reference, this sort of high-level processing procedural logic. Now, what really is the necessary link for this to be really good is to establish the community-wide contributions and also utilize this daily. And we're sort of doing that. We have, as you will hear this afternoon after lunch, we are working on a diffraction processing package, and we're sort of using that every day. Okay, now for the processing philosophy. This is now the plan. And this is not implemented, this is the plan. So down here you have an electron density map, and you want to interpret that to build your structure. So how do we get there? Now one side is what we refer to as image processing. And here's really where we've reshuffled some concepts. So you start with an image. And the first thing we want to do is correct for the optical artifact. So everything that the instrument does to torture our images should be removed first. The second step will be the correction of any sort of crystal distortions, commonly referred to as unbending. Then, once this is done, we extract the reflections, we scale and merge them. And here at this step we have our HK, the amplitudes and the phases, and our lattice line in the continuous range. Yes, please.
I remember that people actually tried to do this before, trying to correct the CTF on an entire image, and then go on from there, especially in single polygon. It never really worked.
I have slide a few steps ahead to talk about that, and tomorrow 1 hour to talk about that as well. So you're right, that's a difficult step, but we think it is necessary. So then here, the last step is what is commonly referred to as discretization, where you go from Z star to L. And then you just put this in a Fourier transform, have your map, and interpret. But as we already realized, there's an alternative approach, which is processing of diffraction patterns, which is sort of similar, actually easier, because you don't have to deal with this. So you extract your reflections, you scale and merge, you discretize, and here you're at almost the same step as here, except there's something really missing, that's the phases. So there's the phasing step, and then you can actually go to the interpretation. And the obvious thing would be, as we've heard several times, in molecular replacement. But now this is way too linear and way too simple. And especially in the discussion with our collaborators, we realized there's sort of loops and possibilities to do this several times over, and this is what these arrows refer to. Now, this is not sketched out. These are just possibilities, to go back from your electron density to the scaling step, or to maybe have some information about how to correct for the optical artifacts. You also have the steps where to go from the amplitudes to the image process data, or here from the discretized to here to merge in the amplitude. So you have not a linear processing scheme, but you can go around and around in circles forever and ever and ever, hopefully getting improved data. Now, one thing I find very important, this is actually a result, this graph. We see this as a result because it's been several hours, days-long brainstorming sessions over the last 2 years, and I had another slide which I didn't put in, which is the detail of how we now distribute the task. Because you see, each of these boxes is fairly independent of the other one, so you can just give this out to collaborators. And I want to focus on this thing here, which is the unbending scheme. It's also a plan. And again, it's compartmentalized. So we start here with an image which is distorted, and we want to find the unit cell positions. Then from the unit cell positions, we want to create this continuous displacement vector map, and once we have that, actually want to do a transformation to get the image in a perfect state, and then continue here. Now there's various ways how you could do that. Some of them are implemented in the unbending, some of them can be thought of new. And 3 of the 4 groups that you saw, Stockholm and Frankfurt and Madrid, are in fact working on this, because we believe this is a very critical step, and there's a lot of improvement possibilities over the currently available algorithms.
Can you give an example? That's just a 2-dimensional spline, right? So how can you improve that?
Well, each of these steps here, so for example, to determine accurately the unit cell positions. Right now, the profile fitting, as Remco tells me from Frankfurt, is done really badly. And if you just take a Gaussian to fit the profile of your cross-correlation peaks, you might get better positions. Then,
so that's what they do, right?
Well, I can only quote Remco, who's been working on this for 1 year, and he says, in this step alone, to determine the unit cell positions accurately, there's a lot of potential to be fixed and to be added.
So incorrect for translational error, not incorrect for rotation?
Not yet. This is what our guys in Madrid are working on. That is here has something to do with the reference and how to find the unit cell positions. So you can create a reference here from a model and then go out of plane and actually detect out of plane variations. But that also means that you have to sort of chuck this up in patches, and then you go back and you process each patch individually. So this is what I mean with this is a result, because now that we have this sort of flow and this top-level vision, each collaborator goes back, hacks his stuff together, tries it out, and we can then all plug it back into the overall processing scheme. Now in Stockholm, they're working on multivariate statistical analysis, and that comes very close to single particle already, because they cut out these patches of crystals and do intricate analysis to see variations. And that again leads to patches. There can be some areas of the crystal that are bent like this, another that's bent like this, and you don't want to unbend them together. You want to separate them first and then unbend them. Well, ultimately, correlation averaging down here, if it's really bad, we just go to what the single particle guys do, just add up individual unit cells or maybe a 3x3 patch of units.
Can I just ask on the philosophy here? So I can understand that you might want to separate unit cells which are not of the same orientation as the bulk of the unit cells you're looking at. So is the philosophy one of removing the ones that are different? Or do you actually try and calculate tilt angles for the two different populations or different populations and merge that in the final?
So I would say that is not decided upon. Personally, I would rather tend to include all the data if possible and not throw away anything, and only really throw it away if there's no way to put something in.
And the single particle approach will also work at highly tilted samples?
That's a good question. I don't know. This is the plan. And right now we have very promising results for 0 degree, extremely promising. I do hope the guys in Madrid get their paper out very soon. I didn't bring any slides, so I can only sort of superficially summarize what they've done. But we all know that tilts are more difficult. So the next thing they'll tackle is the tilted images for their approach.
I don't know that anybody's looked at that at high resolution, but in negative stain, the correlation approach, works perfectly fine at high tilt. So it may be resolution problems that kick in, but there's lots of very old data that's done correlation averaging on crystals at high tilt.
Now, what you just asked before, it's this image distortion correction, and that's again the plan. Now, why do we want to do that? And the reason for that is very simple. We will see this slide tomorrow again. Now, this is the point spread of a single sample point on your measured image. So imagine you would have a sample where everything is empty and just have a very, very tiny sample point. And this is the point spread you generate on your final image. And no, in X and Y direction. So you can see here, this is 100 angstrom, 100 angstrom. If you have a sampling of 1 angstrom, you have a 200 pixel wide or even more point spread on your sample. Now if you do unbending and you interpolate, distort patches, whatever it is, and you have not corrected for this, you're effectively destroying the high resolution information. So we see it as absolutely vital to correct for this first before you manipulate the image.
So why did people then get high resolution data if they destroy it with this technique?
You want to hear my theory about that? If you collect enough data, you don't destroy it, you just seriously scramble it. So if you have enough information, you have a partial truth and the rest is sort of randomized noise. But if you average over that, the actual data is, emphasized more and more, and in the end, you can get a data set. This would mean if this is true, if our concept holds, then you need much less data to have a full and complete data set, which also much better data quality.
So you have some initial results that would confirm your theory?
Which I will show tomorrow.
So the point spread function of 1 point is
then limited in size, or does it continue out to higher resolution?
Well,
That's in real space.
this is in real space, yes.
So shouldn't it be pronouncement for it to say continue? Or does it just stop there?
Well, I think that might be a plotting artifact. So this is like if you integrate over that, maybe that's like 99% of the information is contained here. Here it's obviously cut off, so I don't know how far it continues. It basically is to make the point, if you have 200 wide pixel spreading of information and you move around little patches before you correct for this, that just calls for disaster.
I think the reason why it runs with material what I've seen is that almost no unbending is required, or at least the unbending between neighboring 25 pixel blocks is very little different, and so the damage you do to your price spread function is almost negligible.
Absolutely, that's correct.
If you have a badly ordered crystal, then you cut this in pieces.
But if you have all the crystals, you never get the high resolution. So that's a sort of the organ.
Yeah, not yet.
But that's what your experience tells you. But your experience is based on using software that does not try to do this. So
you see the order directly removed from the sensor signal.
Yeah, but if it's single particle thinking that you 4.2 angstroms, why shouldn't you be able to do this with a badly ordered 2D crystal?
Because then the unbending is the wrong approach. And you have to do correlation and
which comes back to the other slide I had, is that we want to have a setup where you actually decide per image what do you do. You can have some patches that you need to do in correlation averaging, some others that you can still process with the unbending. But just to, not to have one or the other, but to have possibly all of them. Okay, so much for the processing philosophy. Yes,
So one more question about it. So your promising result were test done with the test with prior image or negative?
So my promising results that I will show tomorrow are only numerical simulations on 1D, and tomorrow you will see why we only have that so far. It's rather complicated. We've only just started to use images. Now to the software. I could also spend, write a lot of philosophical words on why and how we designed this. And this is a very compact summary of IPLT and what it should provide and why it provides it. So,
what does it mean of IPLT?
Image processing library and toolbox. So let's see. First and foremost, we want to encourage development of novel methodology. We provide some basic set of functionalities. It is completely modular, so it should be, and I hope it is very easy to extend into custom. It should appeal to novice and expert alike, and it's something that is very, very important from my point of view, since in my experience, scientists can be good scientists, and it doesn't say they're good or bad coders, or that they write good or bad scripts. You get this whole grayscale. And I see every user as a potential contributor. I do not have this dichotomy of a programmer and then the user community telling the programmer what the heck to do. I think it should be a shared effort and everybody can contribute. In the same way, we want to facilitate the easy sharing of these algorithms. So, of course, this stuff is all open source. We want to harvest the creative potential of the community because a single group can never match that. Just look at the X-ray guys. Now, there's 2 X-ray mafias, maybe even more, but there's at least 2. So there's the British Scandinavian mafia and there's the US mafia. But each within them, they have so much manpower and they constantly battle each other over the best programs. And for me, that's one of the main reasons why X-ray has such powerful techniques. Now, of course, you showed on the first day that the number of groups in our field is very, very small. So basically, we have no other chance than all pool together. So we cannot even afford to create 2 mafias, although I'm sure they are, but I'm too young to know that. But we should still pull that together. So that's also our underlying philosophy, right? To make it very easy to do that. And we have a web portal for that. Not as sophisticated as 2DX activity. Now this year, provide a more attractive next generation software. So everybody among us that has coded or tried to code or extend MRC will know exactly why we put this in. So first of all, we really go fully with object-oriented design paradigms. And I know the camera is running, but this is the 21st century. I don't want to see any procedural code anymore in scientific software. I will discuss for hours whether Fortran is still faster than C++. Gladly. Of course, we need a comprehensive documentation and a linear learning curve. Henning was with us, and I could observe the learning process of MRC, and it's what I call a druidic knowledge spread. So you sit next to the expert, and he whispers the secret of the software into your ear. That's simply unacceptable to have this widespread. And think, events like this workshop is exactly what we need to go away from this. Now, there are multiple interaction levels. I have a slide on that later. And of course, cross-platform, same. I don't care what you do, just process your stuff. Now I'm too old for the religious wars on platforms. I did that when I was below 30, discuss about Apple and Linux all the time. Now, tailored to our community, well, the zillions of existing image formats, of course, we did not create our own one. Accommodate the huge images, 10K, 16K square, 16-bit grayscale is rather huge. And do we have a talk about the EBI?
Yes, we have. Yeah.
We have, okay. So there is an EBI XML format for submission of data, and so we just said, okay, we'll just go with the XML stuff. Now here is a compact summary of the IPLT architecture that should tell you pretty much everything. It is built from two languages, C++ and Python. And these languages are perfectly suited to live next to each other and to complement each other. Now, we're using a fair set of tools that are open source and available. Built upon this are our low-level input-output routines, the wrapping of XML, geometric library like vectors and matrices and stuff. Then we have here the base, which is really the core. There you would have something like the image object. The image object is so fundamental, but this actually is more complicated because we have an image and an image state, as you will see in the next slide. Then, orthogonal to that is the whole set of algorithms. So the image is really stupid. It doesn't know how to do anything. It just sits there and can take values and spit out values. And the algorithms do all the work. Now, here you have a graphical user interface, which is sort of optional, but it is still an intricate part of the system. Now, we have a wrapper layer here, which means that a lot of this, pretty much everything, every class, every function is reflected into Python. So whether you're programming in C++ or you're writing a script in Python, it's pretty much the same thing. Based now on this wrapper layer, here we have Python procedures and applications. So this is basically where the processing logic will be implemented, and after lunch I will show you how our diffraction processing is exactly implemented on this level. And this is also where the user interface is. Here's the user work with Python. And here is where you find all the building blocks. So just some code for you to get a feeling about how you would use this. Now this is a mixture between programming and using a script. As I said, it's a continuous flow. You don't have the dichotomy of executables and shell scripts, but it's a continuous range. So as you read this, this is Python code, this is C++ code. First of all, I shouldn't need to explain this because you can read in plain English what this does. The second thing is what you should see if you program in Python or in C++, it's the same except for syntactical differences. And that also means if you would like to contribute, but you're hesitant about the C++ stuff, you can start off in Python, sort of, after a year or two, decide you want to go to C++, you find that the syntax is exactly the same. So this language barrier is reduced as much as possible. All right. There's no way that I can explain this slide. This is meant to impress you that actually the software is very sophisticated. Because on the high level, what you're dealing with usually as a normal user is an image, it's an image, plus a set of algorithms. And those are very safe to use. You cannot crash the machine. But the downside is it's a little bit slow because there's error checks. Like do you write out of bounds, it doesn't work. Of course, that's been accepted for people that do the real algorithm because they want to write to memory directly. All object-oriented stuff aside, it's still very satisfying to write directly into a pointer, and that's as fast as you can get. So we have this underlying image state and algorithm state architecture, which for the C++ knowledgeable people is a templated set of image states that are all encapsulated by one image handle. So whether you have a spatial image with real numbers or you have a complex half-frequency image, you don't have several classes, you have one thing, you just have an image. And the image keeps track of what the heck it is. You don't have to worry about that. If you do an FFT on an image, it just changes state, and you just do an FFT again. So as you saw before, our FFT algorithm does not have a direction. It's not necessary to say forward or backward FFT. It's implicitly known by the state here. And so what do we have? We have a fairly vast set of functionality already, and again, this is one of the slides that's supposed to impress you that I've been working really hard. And this afternoon I will show you for the diffraction processing which set of these classes and routines we're actually using, and you will see that it's more than 50%. So every processing pretty much uses a large set of functionality that is available. Now, all of this, okay, the wiki comes first. So, this is all done. Now, what are our first collaborative steps? There's no way that we can force everybody to use IPLT, and actually we don't want to. So in this EU thing, the guys in Madrid have a fantastic single particle package called XMIP. And through some heavy evangelizing on my part, I convinced them that they might consider adding a Python interface, and because their stuff is C++, it was rather easy. So now they have this Python interface. Now in our lab, Andreas Schenk, we are using MRC. So there's the MRC executable, but we have written a Python wrapper to funnel all the commands into the executables and run them and extract the results. So as you see, here's IPLT, here's XMIP, here's MRC. We use everything from Python. No need to switch back and forth between executables. Just have everything over Python. Now, all right. I think I'll take this one first.
So, same question as before. So there's another try to get Spider and Eman and so on together. There's also some thinking about putting XMIP together with Spider, Freeline, all these other.
What is required to do that is here what you see as conversion layer. And what this means is that each package has their own image format, some low-level implementation.
And so nobody still couldn't figure out the joint image format like this?
It is not possible. I've been at least 3 workshops that deal only with the unified image format. And your regression level is this high after each one. So basically the bottom line is it's not possible. And we're not going to do it.
It's worse than rival mafia.
Yes. Yes. So that's, but what you can do, what you can do is make it easier for the normal user. Because here you have a conversion layer, so XMIP and IPLT know how to talk to each other on the low level. Now the user that is up here on the Python level just says, oh, I want to have the IPLT image and I want to have the XMIP image. Runtime, in memory. No import, export needed, nothing. Now if Spider and Eman agree to the same thing, and these kind of conversion layers are fairly simple to write. It's like 1 or 2 days if the people that are involved in the project do it, because they know their format. I see no problem in adding all the Python compatible packages. And this is what I meant in the beginning. The structural biology community is moving to Python. So when we evaluated our options 3 years ago, we said, hey, it has to be Python because everybody's moving here, especially the X-ray guys, and they sort of set the pace for the new development. So, yeah, this is quick. Now, if you want to contribute, no, you should contribute. I beg you to contribute. That's the whole point of this. Now, what can you actually do? You can do a lot of things. On the Python level, you can hack little script jitters to be run in batch or in interactive or in graphical mode. You can implement more involved processing logic like we did for our diffraction processing. You can create custom graphical user interface components using WX-Python because the underlying thing is in WX-Visions. So just open a window, add a few buttons, all in Python, all interactive. On the C++ level, You can add graphical user elements, either as overlays, don't have time to go into that, or standalone videos. You can implement high-level algorithms using this image handle thing, which is very safe to use and easy, but a bit slow. Or you go hack into the low-level algorithms with templated C++, all the nice stuff, very fast, gives you core dumps very easily. And please feel free to muck around with the core libraries. You know, everything is documented, everything is open source. If you find a bug or an improvement or whatever, no problem. So in this EU context, what are we actually doing? Where are these contribution layers? And you can see they're all over the place. Well, here I'm doing low-level refactoring based on the feedback. We're providing this interoperability. Here we have this wrapper. I'm writing some GUIs here. Guys in Stockholm are using NumPy to implement their MSA routines. And here we're doing the low and the high level algorithms for diffraction processing. So pretty much you can start anywhere you want with this. We do have an online wiki, which is growing by the minute. Well, sort of the concept that you just go in, the pages just start to appear and people can edit it. So you can go in there, you don't have to register nothing if you find a typo or want to ask a question. And I'm trying to force the guys that work with me and actually myself to, when we're done with something, to go in and add an entry. If you go there today, you will find it is not empty, but it could be filled with more info. And in fact, I'm trying to put the information about the diffraction process from this afternoon onto here. This is why I will not have a handout, but I hope that you can, when you come home, look at this and get it directly online and add comments if you want to. Okay, this is my last and favorite slide. These are my recommended C++ books for all of you that want to get seriously into development with IPLT. And I really recommend them to any programmer out there, because you will find that if you go from the procedural world to the object-oriented world, things become much easier, exactly in the way that Brian said in the beginning. This Apple philosophy, this encapsulation philosophy, this is what object-oriented design is all about. So we can work with several people, each working on a little thing. We don't have clashes, we don't have conflicts, and if we do, they're rather fairly easy to solve. And I will go back to that slide so you can write it down. These are, again, the people that are involved in this, in Andreas Engel's group, in Madrid, in Stockholm, and in Frankfurt. And I must mention the sponsors, the sixth framework of the EU, because they might also watch the tape when they find out that I was here and they're paying for all of this. So I need to acknowledge them. And I have 7 minutes to take questions. Thank you very much for your attention.
So if you've got this stuff up on the website, would you like to go to the web address perhaps for that wiki?
There it is, IPLT.org. Of course, I selected the abbreviation after checking that it is actually available as an org domain. So like 10 names were rejected because they were already taken.
So I might have missed it, but how is this linking in the X-ray?
I'm sorry?
Is IPLT also going to be linking in the X-ray community? I might have missed it in one of the
Yes, in a way. As you will see after lunch, for the diffraction processing, the image processing, our reflection data is stored in a standard CCP4 MTZ file. And one of the things we've created is a wrapper around that CCP4 library. So that's right now the only link. But of course, if the X-ray community has these Python modules, you start Python, you import IPLT, you import a Phoenix project, and you run them both at the same time, sure.
And one other question related specifically to electron crystallography. What do you see as the major advantages in algorithm development in your type of pipeline compared to what's out there? Can you give us maybe 2 or 3 examples of where you see some major improvements?
It's, in essence, the modules that I've showed you, because after this brainstorming discussion with all these guys, we decided to focus on the unbending very heavily, and also on this TSIF, this tilted contrast imaging function correction that I will present tomorrow. Then the other thing that I didn't mention, and I have sort of a gut feeling that there's room for improvement, is the discretization. So the lattice line fitting gives us at least headaches in the lab, and I think a lot of things could be done for that as well. But since we haven't evaluated that, I'm not really sure, it's just a gut feeling. But I think that the unbending and the TSIF correction will give us higher resolution ultimately. So treat the data in a better way.
Just add another reference to that C++ page. I did notice numerical recipes in C++, which I think is probably a definitive scientific programming guide for C++.
Absolutely, yes, thank you.
More open question. It's to the audience concerning this idea for you to work with, I would say, bad crystals improved by the processing quality of the data. That's one of the points that you mentioned, and the end it would. In our hands, my point of view for the crystals that we have in the grid are on three categories. Either you have the crystals that are, let's say, around 20 angstrom resolution or 15. Okay. The other category are those that are around 10 or 7 angstrom that you can do a 3D map, and the exceptional 2D crystals. So there is not continuous quality of crystals from 20 to the exceptional. So there are three different things. And you think that with processing, a better processing, we can go from one type of crystals to another one?
You can never get more out of the data than there really is. But I remember frustrations that we had in our group where you know that you have 3 angstrom data and you hit a brick wall at 6 or 7 during processing. That's the sort of thing I'm talking about. You know that there would be more there, but the darn thing doesn't come out.
That's interesting. How do you know it's there by the things you don't get out? Does it never have? This is very interesting.
So when you know that you have the information in there, you always get it out.
Yes, otherwise I wouldn't have the information in there.
And maybe we just had an exceptionally difficult project.
No, how do you know that the information is there if you don't get it out?
Now, what I mean is the information is there in the diffraction patterns or in the images, but the map does not reveal. I mean, you know when you see a map, if you have 4 angstrom data in there, ultimately the resolution is determined by what you can do with the map. So if you see your images and you know that you have the information, but the map looks crappy.
So how do you know from the images that you have the information?
You know where the reflections go, right?
You mean like if you've got a 6 angstrom diffractive crystal or something like that, you can't see up into a 6 side?
Yes.
Yeah.
Okay.
But I have one question. You said any information you can tell from the diffraction pattern. If the crystal is badly ordered, and for example, several pieces of crystals, actually each pieces are very good, but in diffraction
No, this was a general statement that if you're doing the processing in any step, you start to get a feeling for the project, what sort of information you could extract. And one of the reasons I was hired by Andreas is because he said he has this large frustration that he sees these excellent crystals and he sees these excellent individual images, but at the end, we cannot build atomic resolution structures based on our densities. So there must be something along the line that is not working correctly. Now, I don't know what it is. Our working hypothesis is that through these various improvements in the processing pipeline, we might actually improve it.
So how many cases of this did you really have? The only case where I'm aware of something like that was actually your Shizoko 4 crystals, which you got beautiful diffraction to go nose work, but you couldn't merge it. But this wasn't an image processing problem, this was because the crystals had effects that you couldn't see in the diffraction. And I think the only case that I'm aware of is local boring crystals, and might well be the same problem that they have in Japan. But that's not an image processing problem, that's a crystal problem.
Yeah, Crotox is exactly
It
the
is
same.
another one.
It's the crystal, not the data processing.
Okay.
Well, we have a double layer of this, so they might be more sturdy. Aquaporin crystals might be more sturdy because we have a double layer.
Yoshi's crystals were double layers, that caused the problems because they were actually shifting on top of each other. Crotex is the same.
How many people?
And I think what is strongly that you not exclude any information you can get from a crystal. You can get the input from images, take it to life, you can put in diffraction pattern. That might be an advantage for crystals, which are very difficult to crystallize.
After one image sample is burned, you cannot get the diffraction pattern anymore.
But what Yoshi did was actually the opposite way around. You first got a high resolution diffraction pattern, then took an image, and based on the faded information, you could actually categorize the crystals, and then only use one category to merge the X-ray, the direct diffraction. It was a huge amount of work.
One other point, I think I've not been to the IPLT website, so I don't know how. I mean, is it actually up and running and functional, or is this still at the development stage?
It's up and running and functional. The wiki is there, and it needs to be filled more.
No, the actual program.
Oh, it's all there. Everything that I showed you, you can download and compile and run. So just for this workshop, we worked really hard for the last 2 weeks to get all our developmental stuff into the main release and to test it. And also everything that I will show this afternoon, it's all available, open source.
I have a question. I have like impression that your software is a collection of image process tools, whether or not they are necessary for project. For example, you have Canyon, like that is
We
used
have
for
an edge, yes, but which we use to detect the beam stop in our diffraction patterns.
that is used for diffraction.
Yeah, so we have like a dual top-down, bottom-up approach. So we have a top-level design that is really nice, but then we say, hey, what do we need for diffraction processing? We need this and this and this and this and this, and then we implement it. But we implement it in a generic way that is available as a class library. So this thing is just emerging, and now when we implement image processing more, going to be 50 more algorithms that we need just for that. But you can use it for other purposes as well. Yeah. So it is a generic image processing library that is very much tailored to the electron crystallography or to EM processing in general. But it's not exclusive for sure.
Just for example, in 2DX, you get systematic area about the processing steps. Do you have the same idea, or you just put everything there, give to the user to?
I will show you after lunch that is indeed what we do as a second step on top.
Who's a collaborative effort? How many people are practically working on it? How many full-time programmers?
Well, there's no full-time programmer. It's scientists that know how to program. We would love to have the money to pay a full-time programmer, but we don't.
How many people actively are involved?
In our group, 2, 3, 4, 5. In Madrid, 1. In Stockholm, 2. In Frankfurt, 1. I didn't keep track of what I said, so it's below 10. And that's the reason why I'm here, and I'm very glad that Henning invited me. There's, just hopefully maybe 1 or 2 among you that is interested. Please contact me, and that would be excellent. I do think we should be aiming for longer.
Yeah. So we have to thank the different speakers for this session. I keep in mind that the main bottleneck of 2D crystallization, which is formation of 2D crystals and image processing, are huge effort of the European world community, and I guess thank you again.
I would like to make something. I think the most important
concept.
So we have a good job.
We realize the structures and the pictures of the structures. Yeah. So we cannot afford to have the MRC folks, the 2DX folks, and the IPLT folks. That will kill us all. So I think we need to take what is best from everything and use it together and try to exchange and build. And that's what I think we need to start.
Yeah, but see, this exchange is on several levels. It's not necessarily just the software. It can be just GUI interface. I mean, I've seen some stuff in 2DX which I find extremely impressive, which we would never have thought of. And it's also these little things that are very important, not only the executables underneath.